Hello students, we are now studying second chapter multi-stage amplifiers. In this chapter we have studied multi-stage amplifiers, different type of multi-stage amplifiers like RC coupled amplifier and transformer coupled amplifier. In the today's class we are going to study the construction, working of multi-stage amplifier and also its frequency response, advantages and disadvantages, and applications of direct coupled amplifier. So by the completion of this class you will be able to know the direct coupled amplifier, construction, circuit diagram of direct coupled amplifier, operation of direct coupled amplifier, that is working of direct coupled amplifier, the frequency response of direct coupled amplifier, advantages, disadvantages, and applications of direct coupled amplifier. So what is a direct coupled amplifier? In a multi-stage amplifier, if one stage is directly connected to the next stage without any coupling device, it is known as direct coupled amplifier. So in a multi-stage amplifier, if one stage is connected, if one output of one stage is connected directly to the input of the next stage without any coupling devices, then the amplifier is known as direct coupled amplifier. So in many number of applications it is required extremely low frequencies signals that are to be amplified. Examples of very low frequencies are photoelectric current, thermocouple current, thermocouples, where the signal generated with very low frequencies. So to amplify these frequencies, signals with very low frequencies, the capacitor coupled amplifiers, RC coupled amplifier, is not suitable because it is going to offer very high reactance to the low frequency signals. So at low frequencies, capacitors and transformers are not used as coupling devices, and because the size become very large, so such cases we are going to use a direct coupled amplifier for amplification of extremely low frequency signals. See, this is a circuit diagram of a direct coupled amplifier. See here, this is the first stage, second stage, third stage. So the amplified output of first stage is directly connected as input of the second stage. Similarly, the amplified output of the second stage is connected. The amplified output of the second stage is directly connected as input to the third stage without any coupling devices between the first and second and third. You can see there is no coupling device, directly they are connected. So hence it is known as a direct coupled amplifier. So here it is a 3-stage direct coupled amplifier. It uses complementary transistors, NPN and PNP transistor. First stage uses NPN transistor. NPN transistor. Second stage is using PNP transistor. Again, third stage is using NPN transistor. And so on. So every alternate stage of NPN we are going to use a PNP transistor and so on. The output from the collector of the first stage transistor T1, the output from the collector of the first stage transistor, the output from the collector of the first stage transistor is connected directly as the input of the second stage transistor T2. The output of the collector of first stage transistor T1 is directly connected as input of the second stage transistor T2. And so on. Here the weak signal is applied at the input of the first stage transistor T1. The signal to be amplified is applied to the input of the transistor T1. Due to the transistor action, due to the transistor action, an amplified output is obtained across the collector load RC of the transistor T1. So when we give a weak signal to the base of the transistor T1, first stage transistor T1, the amplified output due to the amplifier action, the amplified output is obtained at the collector resistor of transistor T1. So when we give the signal, input signal here, due to this transistor action, the amplified output will obtained across the collector resistor of transistor T1. This voltage drives the base of the second transistor, and amplified output is obtained across the collector load. So this amplified output of the first stage transistor, the voltage which produced across the collector resistor of transistor T1, that is the amplified output of the first stage, going to drive the input of the base of the next stage transistor T2. So therefore, that due to the transistor action, this amplified output of the first stage coming from the collector load of transistor T1 gets amplified by the transistor T2, and the amplified output will get at the collector load of the transistor T2. And this amplified output of that second stage at the collector resistor of transistor T2 drives the input of the transistor T3. So therefore, due to the transistor action, the amplified output is obtained at the collector resistor RC of the third stage transistor T3. Thus, the direct coupled amplifier raises the strength of the weak signal. So what happens here is the DC voltage at the collector of the first stage reaches the base of the second stage. So proper designing is needed. See here, the overall output will obtained at the collector of the third stage transistor T3, but the overall gain of the three stage transistor amplifier is always less than the product of the gains of the individual stages, because the DC voltage here, the DC voltage at the collector of the first stage reaches the base of the second stage. The DC resistance of the first stage, collector of the first stage, reaches the base of the second stage. Similarly, the collector resistance of the output resistance, the DC output resistance of the second stage reaches the base of the third stage. So that is going to alter the operating point. This DC voltage will alter or will disturb the will change the operating conditions of the next stage. So previous stage is going to affect the next stage DC conditions. So we need a proper biasing is needed to operate the direct coupled amplifier, otherwise there will be a distortion in the direct coupled amplifier. So this is called as a drift problem. This is the drawback of the direct coupled amplifier. We call it as a drift problem in the direct coupled amplifier. So the drawback of the direct coupled amplifier is the parameters like VBE, base emitter voltage of the transistor, and beta, that is current gain of the transistor, vary with the temperature. You know, the beta and VBE are the temperature dependent parameters of the transistor, of any transistor. The VBE and beta of any transistor depends on the temperature. These are the temperature dependent parameters. This causes the collector current and voltage to change with the temperature. This VBE and the beta of the transistor varies with the temperature. Due to this, the collector current and the voltage going to change with the temperature. This voltage change appears at the final output. So therefore, because of this, the unwanted change in the output voltage, this unwanted change in output voltage which has no relationship with input is called a drift problem. So this drift problem can be overcome by using complementary transistors in the multi-stage amplifier. This makes the circuit using these complementary transistors. We can avoid the drift problem in the direct coupled amplifier. These complementary transistors, using of these complementary transistors makes the circuit stable with respect to temperature changes. So because of this NPN followed by PNP, we are using. The direction of collector current increases beta. The collector current increases beta when the temperature rises in opposite for the two transistors. The direction of the collector current increases current increases the beta when the temperature rises. When the temperature rises, the beta rises, but the direction of the collector current is opposite for the two transistors. So this, because of the direction of the collector current increases in opposite directions, because of the increase in temperature with beta, so these two collector currents will cancel each other. Then we are avoiding the drift problem, so that there is no drift from the change of voltages, operating voltages with the temperature. So this is the important consideration in the direct coupled amplifier. We are going to use a complementary transistors in the design of multi-stage amplifier, direct coupled amplifier. So if first stage is NPN transistor and second stage we are going to use PNP, alternate stages we are going to use NPN and PNP transistors that are going to reduce the drift problem in the direct coupled amplifier, because of the property of the direction of collector current. Though beta of the transistor NPN PNP with temperature increases the collector current, but the increase in the collector current, direction of the collector current is opposite in the NPN PNP transistor, and that's cancel each other, thereby removing the drift in the direct coupled amplifier. Coming to the frequency response of direct coupled amplifier. The frequency response is the curve showing the variation of the gain of the direct coupled amplifier with the signal frequency. Here this figure is showing the frequency response of the direct coupled amplifier. Here in the frequency response, the gain is uniform up to a certain frequency denoted by F2 here. Here gain is going to be a flat constant up to this frequency F2, After this, the gain going to decrease slowly. Beyond the frequency F2, the gain rolls off slowly in the high frequency region. The gain rolls off at high frequencies because of the increased emitter diode capacitance and stray wiring capacitance. The gain is going to decrease at high frequencies because of the increase in the emitter diode capacitance emitter diode capacitance and stray wiring capacitances at high frequency. See, with the high frequency we are going to have a capacitance that will come into action at high frequencies is the electrode capacitance between the emitter and base. So we are going to have this capacitance, electrode capacitance will come at high frequencies. Here electrodes of the transistor acts as positive and negative plates. Base and emitter acts as electrodes. Base and emitter terminal of the transistor acts as electrodes or plates of the capacitor, and the air between the two terminals acts as dielectric. So this called as electrode capacitance will come at very high frequencies. And also at very high frequencies the stray, we have a stray capacitance, unwanted capacitance. Stray capacitance also going to effect will come. So here any junction, junction of the two wires, when two wires are joined at one point, so at the junction wiring we have small air gaps at the junction. So one wire acts as positive and another wire acts as a negative, and the air gap that going to exist at the joining of the two wires acts as dielectric. So this is called as stray capacitance or wiring capacitance. So that will come at very high frequencies. So these two frequencies going to act as a short circuit for high frequencies. So therefore the signal gets bypassed without the amplification with the transistor. So the gain rolls off at very high frequencies because of this electrode and wiring capacitance in the circuit. Advantages. ఏంటిది ఇటు పక్క పెట్టు, అటు వెనుక పెట్టు, ఆ ఇన్వర్టర్ వెనుక లోపలికి కొంచెం పక్కన పెట్టు, కింద పెడితే దేనికి. Coming to the advantages of direct couple amplifier. This circuit arrangement is simple because the minimum use of resistors. The circuit has low cost because of the absence of expensive coupling devices. it can amplify very low frequency signals down to zero frequency. Very low frequency signals we can amplify because of the absence of the capacitors. It is going to amplify very low frequency signals down to zero frequency. So the advantages are circuit has a low cost because of the absence of coupling devices, but expensive coupling devices like transformers and capacitors. The circuit arrangement is very simple because of minimum number of resistors are required, and this circuit is able to amplify very low frequencies, extremely very low frequencies down to zero frequency, which is not possible with the RC coupled and the direct transformer coupled amplifiers. So the disadvantages of this direct coupled amplifier are this direct coupled amplifier are not used for amplifying high frequencies because of the gain rolls off rapidly in the high frequencies, and not going to use this direct coupled amplifier for amplification of very high frequency signals. And operating point shifted due to temperature variations because they are directly connected. One stage is connected directly to the input of the next stage, so the operating point shifts due to temperature variations of the temperature dependency of the transistor parameters. So this is the drift problem. There is small operating point gets shifted due to temperature variations. Applications of direct coupled amplifier are analog computation, they are going to use in power supply regulators. Direct coupled amplifiers are used in bioelectric measurements like measurement of ECG, amplification of ECG, EEG signals, where the frequency signals are very small frequency signals that are generated in the human body, that we are going to amplify using this bioelectric direct coupled amplifier, that is bioelectric measurements. Linear integrated circuits, we are going to use this direct coupled amplifier. So in this topic, so far we have discussed the circuit, the direct coupled amplifier, the circuit of a direct coupled amplifier, the circuit analysis or the construction of the direct coupled amplifier, the operation or the working of direct coupled amplifier, the frequency response of direct coupled amplifier, advantages and disadvantages of direct coupled amplifier, the drift problem that exists in the direct coupled amplifier, and also the how to reduce the drift problem in the direct coupled amplifier using complementary transistors in the alternate stages we have studied, and also the applications of direct coupled amplifier. So small quiz questions on the topic. Direct coupling is used for amplifying low frequencies. At extremely low frequencies, the electrical size of coupling devices become very small, very large, so it is very large. Questions frequently asked on this topic, frequently asked questions. With a neat circuit diagram, explain the operation of direct coupled amplifier. Explain the drift problem in the direct coupled amplifier and how can we overcome this problem. List the advantages and disadvantages of direct coupled amplifier. List the applications of direct coupled amplifier. So far we have studied three types of in the multi-stage amplifier. We have studied three types of coupling, that is RC coupled amplifier, transformer coupled amplifier and direct coupled amplifier. Now we will compare these three configurations. The comparison parameters are with respect to frequency, with respect to cost, space, impedance matching and the applications. We are going to compare these three types of multi-stage amplifiers: RC coupled amplifier, transformer coupled amplifier and direct coupled amplifier will be compared. With respect to frequency, RC coupled amplifier is excellent in audio frequency range for amplification. Transformer coupled is poor, and the direct coupled amplifier is somewhat better with respect to frequency range of amplification. Excellent is the RC coupled amplifier in the audio frequency range. Transformer is very poor, not going to amplify a wide range of frequencies using transformer coupled amplifier, and it is better in the direct coupled amplifier. Coming to the cost, the RC coupled amplifier, the cost is less. Transformer coupled amplifier cost is more, and direct coupled amplifier is least. The cost is very small, or the least in the three types of multi-stage amplifier. The cost is least in the direct coupled amplifier because of the absence of coupling devices and less number of resistors. The space occupied by the three types of amplifiers, the space occupied is less in the RC coupled amplifier. It is very high. It is more in the transformer coupled amplifier because we are going to use the transformers, so they are bulky, so this occupies very more space. And the direct coupled amplifier is least in the space because the absence of because of use of less components in the circuit, absence of bulky coupling devices, the size is least among the three. Impedance matching is not good in the RC coupled amplifier because the output resistance is of RC coupled amplifier is of the order of few kilo ohms, and load resistance is of the order of only few ohms, so it is not good for impedance matching. Transformer is excellent impedance matching. So by adjusting the turns ratio of the transformer, we're going to match the load impedance to the output impedance of the circuit. RL dash is the output resistance, is made equal to the RL load by adjusting the turns ratio N. By adjusting the turns ratio N square, that is N1 by N2 whole square. RL dash is equal to N1 by N2 whole square into RL. So that is excellent in the transformer coupled amplifier. It is somewhat good in the direct coupled amplifier, the impedance matching. So applications coming to the RC coupled amplifier for we're going to use for voltage amplification, and the transformer coupled amplifier will be used in the power amplification. Simply for amplifying the signals, we are going to use a direct coupled amplifier. So so you will see the calculation of bandwidth of multi-stage amplifier. frequency response of multi-stage amplifier. Multi-stage amplifier's frequency response. See here the multi-stage amplifiers. So the input voltage, the signal to be amplified, is coupled to the base of the transistor using the coupling device C1. So the output voltage we will obtain we can write the equation for output voltage. V0 is equal to Vin into R divided by R minus JXC. So the voltage gain is given by R minus J 1 by omega C, or the voltage gain AV is equal to taking R as common 1 by 1 minus J 1 by 2 pi FC R, or we can write AV is equal to 1 by 1 minus J F1 by F, where F1 is equal to 1 by 2 pi RC, or we can write AV taking magnitude of the voltage in AV, that is 1 by under root of 1 plus F1 by F whole square, and the phase angle is tan inverse of F1 by F. The multi-stage amplifier at low frequencies, if n identical stages are connected together, then the overall voltage gain at low frequencies is given by overall voltage gain in the low frequency region AV low is equal to AV1 at low frequency AV product into AV2 at low frequency, AV3 at low frequency, and so on, AVN at low frequency. That is, if all the individual stages having uniform gain, then AV low to the power of n, AV low is equal to AV low to the power of n. Where n is the number of cascaded stages. Since AV1, AV2 at low frequency, we are taking the similar stages, we are considering the gains of individual stages are equal, then AV low divided by AV mid overall, taking the ratio, that is AV low divided by AV mid to the power of n. that is we can write 1 by 1 minus jf 1 by f to the power of n. AV low by AV mid, overall gain of ratio of overall low frequency gain to the mid frequency gain. Overall it is the ratio of overall low by AV low by AV mid to the power of n. So that is 1 by 1 minus jf 1 by f to the power of n. For lower cutoff frequency AV low by AV mid, overall it is equal to 1 by root 2. So therefore we can write 1 by under root 1 plus f1 by f whole square to the power of n is equal to 1 by root 2. Therefore the lower 3 dB frequency of multi-stage amplifier, a lower 3 dB frequency of n identical cascade stages as FLN, it is the frequency for which the overall gain falls to 1 by root 2 3 dB of its midband value. So therefore 1 by under root 1 plus FL by F of n stage to the power of whole square is equal to 1 by root 2. So that taking to the numerator side, that is 1 plus under root 1 plus FL by F nth stage to the power of n is equal to root 2, squaring on both sides 1 plus FL by F in the low frequency of region of n stage to the square whole to the power of n is equal to 2, taking nth root on both sides 1 plus FL by F whole square is equal to 2 to the power of 1 by n, or we can write FL by F whole square is equal to 2 power n, 2 power 1 by n minus 1, or we can write FL by F is equal to under root 2 power 1 by n minus 1, or FL of nth stage is FL by 2 power under root 2 power 1 by n minus 1. Similarly, we can write the high frequency gain equation for high frequency voltage gain in the high frequency region. So we can write the equivalent circuit in the high frequency region. See here, this is the equivalent circuit in the high frequency region. So where we can write the voltage equation V0 is equal to minus jXc into V in divided by R minus jXc, or AV is V0 by V in, that is 1 by R plus 1 by 1 plus J omega RC, or AV is equal to 1 by 1 plus J 2 pi F CR, or that is 1 by 1 plus J F by F2, or AV is equal to 1 by 1 plus under root 1 plus F by F2 whole square, tan inverse of F by F2, where F2 is 1 by 2 pi RC, So taking the ratio AV high by to the mid frequency overall gain, that is AV high by AV mid to the power of n stage, is equal to 1 by 1 plus j f by f2 whole to the power of n. For cutoff frequency AV high by AV mid is equal to 1 by root 2. So therefore 1 by under root 1 plus fc high by f2 whole square to the power of n is equal to 1 by root 2. So writing in terms of high frequency cutoff frequency of a multi-stage amplifier is f2 into under root 2 power 1 by n minus 1. So multi-stage amplifiers frequency response, the cutoff frequencies for a cascaded amplifier with the identical values, identical stages, the fc1 and fc2 are found using the formula. Lower cutoff frequency of in-stage multi-stage amplifier is fc low is equal to fc1 by, where fc1 fc2 are the identical cutoff frequencies of each stage. So fc low overall cutoff frequency of a multi-stage amplifier is fc1 divided by 2 power 1 by n minus 1, and upper cutoff frequency of multi-stage amplifier is fc2 into under root 2 power 1 by n minus 1, and bandwidth is simply the fc high upper cutoff frequency of multi-stage amplifier minus lower cutoff frequency of a multi-stage amplifier. So when each stage has a different lower upper cutoff frequency, if these frequencies holds good, when each stages are going to have identical upper and lower cutoff frequencies, but when they are different, when the lower cutoff frequency fcl of each amplifier stage is different, then the dominant lower cutoff critical frequency fcl dash equals the critical frequency of the stage with the highest fcl, and when the upper cutoff frequency fcu each amplifier stage is different, then the dominant upper cutoff frequency fcu equals to the critical frequency of the stage with the lowest fcu. So this is the frequency response of a multi-stage amplifier.